In this video, we'll look at the incenter of a triangle. We'll start the video by defining the incenter and looking at some of its properties, and then at the end of the video, we'll do an example. So if you're here for just the example, feel free to skip ahead. So to begin, the incenter is our point of concurrency of the angle bisectors of the triangle. So let's take a look at a sample triangle here, where I'll label each vertex A, B, C, and we're going to draw in our angle bisectors. So let's say we start at some vertex. Let's begin at vertex A, or angle A, and if we want to draw our angle bisectors, we're going to insert a ray starting at A, and when we draw this ray extending out, we want to make sure that it's going to create two sub-angles that are equal in measure. So we'll mark this off by a single arc there. We're going to do the same thing from B, where we're going to draw in an angle bisector. So these two sub-angles are equal in measure. And then we'll do the same thing at C. Now this point, where all of these angle bisectors meet, is what is called our incenter. And we'll label that point I. Now the properties of the incenter that come as a result of these intersections, or of these intersections between all of the angle bisectors, is this point is equidistant from each side of the triangle. So quick side note, when we measure distance from a point to a line, it is assumed that you are going to measure the length of the perpendicular to that line stemming from that point. So we would have to draw a line that runs perpendicular to this, and we're going to measure this length, and that would be our distance from that point to the line. So it's under the assumption, again, that we're measuring the shortest path from the point to the line. So extending that idea over to our incenter, if we're going to measure the distance from the incenter to each side, we're going to draw perpendiculars to those sides. Now the lengths of these three green lines are all equal, and therefore those segments are congruent. So that's the first property of the incenter, and the primary thing we want to be able to use in problem-solving applications. And you'll notice when we insert those perpendiculars, we form these smaller right triangles, and it's often helpful to analyze those triangles to find different aspects that we may be looking for. So I'll highlight one in purple. We have a right triangle right there that pops up. So keep that in mind. The other thing why it's called the incenter is because it is the center for the inscribed circle. So what the inscribed circle is going to be a circle that is on the inside of the triangle, and I'll do it in red to the best of my ability, where it hits the sides of the triangle. So that point I is the center of that inscribed circle. So now that we know what the incenter is, how do we actually find it? So given that we have x, y coordinates for the vertices of our triangle, we can use this formula for the incenter. So the incenter is a point itself, so it's going to be an xy coordinate. So how you get the x coordinate is highlighted in this first section of our coordinate that's modeled by this formula. So what does all this stuff mean? So x sub 1, x sub 2, x sub 3, y sub 1, y sub 2, y sub 3, those are the coordinates that are given to you that represent the vertices of the triangle. So that's where you insert those values. Now what is A, B, and C? So A, B, and C are going to be the side lengths of the triangle. Now what sides you're measuring, let's say we have our triangle A, B, C, where capital A, B, and C represent the angles in each vertex. Side A is traditionally labeled as the side that is opposite angle A. So we'll call this lowercase a, and if we repeat that idea, this side would be lowercase b, and the side opposite capital C would be lowercase c. So we're trying to find the lengths of those sides, and once we find those side lengths, we're going to insert them into the formula as well, and just simplify as far as we can. So as a reminder, to find the lengths of those sides, we're going to have to utilize either Pythagorean theorem or the distance formula. So we'll write distance formula as a reminder, where the distance between 2 points is calculated as the square root of the difference in the x's squared plus the difference in the y's squared. So this is just Pythagorean theorem in disguise, something we've discussed before. If you're more comfortable using Pythagorean theorem, that is also acceptable. So now let's jump over to an example on how to actually find the incenter. So we have 3 coordinates here, and I have a coordinate plane off to the side, and I'm going to plot those points first because we're going to need to find some side lengths, and one way I'm going to do it is using the Pythagorean theorem. So we're going to do -5, 3 as our first point. We'll label that A. We got 1, 7 as our B, and C is 7, -5. So we have our formula, which we'll rewrite again. So as we just discussed, A, B, and C represent the sides of our triangle. So to find side A, we have to find the distance between BC, because BC is the side opposite vertex A or angle A. So this is our side A. So how we're going to find that, let's do Pythagorean theorem, because I know most of you would probably resort to that, and that's why we have this drawn out. So I'm going to make my right triangle. We're going to count off the sides of this right triangle. So this is a 6, and then we have 7 plus 5, so a total of 12. So we know that side A is going to be equal to 6 squared plus 12 squared. So A squared is going to be 36 plus 144. So A squared is going to be equal to 180. So A is equal to the square root of 180. Now we can simplify this square root into 2 and 90, 2 and 45, 5 and 9, 3 and 3. So this is going to be equal to 6 root 5. So we'll write that off to the side where our A value is equal to 6 square root of 5. And we're going to do that same thing for B. So side B is going to be opposite angle B, which is going to be the length of AC. So we'll do Pythagorean theorem again, and then I'll use distance formula for the last one. So we're going to draw our right triangle. We have 3 and 5, which is a side length of 8, and then we have 5 and 7, which is a side length of 12. So again, this is our side B, so we're going to say B squared is equal to 8 squared plus 12 squared. So B squared is equal to 64 plus 144. So B squared is equal to 208. So B is equal to the square root of 208. We can break this down into 2 and 104, 2 and 52, 2 and 26, and 2 and 13. So we're going to have 4 root 13. We'll make that note. And then lastly, we will do C. But this time for C, we're going to use the distance formula. So we know C is the side opposite angle C. And to use the distance formula, we're going to do the square root, and we're going to do the difference in the x coordinates that make up that side. So we're going from A to B. So I'm going to look at A and B. I'm going to find the difference between the x's, and I'm going to square it, plus the difference between the y's. and square it. Now, the order doesn't matter, so you don't have to do y2 minus y1 versus y1 minus y2. Like that order doesn't matter because you're ultimately squaring it. So then we're going to get, negative 6 squared, which is 36. And then we're going to get negative 4 squared, which is 16. So we're going to get the square root of 52. So if we break that down, 2 and 26, 2 and 13, we're going to get 2 root 13. So now let's insert this into our formula. So let's start with, I should have the points visible. So our incenter, this on blue. Okay, so our incenter, we're going to substitute in. So a is 6 root 5, and we're going to multiply that by x1. So what is x1? Let's label these x1, y1, x2, y2, x3, y3. So x1 is negative 5. Then we're going to do plus b, which is 4 root 13, times x2, which is 1, plus c, which is 2 root 13, times x3, which is 7. All over 6 root 5 plus 4 root 13 plus 2 root 13. Over, we're going to do the same thing this time with our y, so it's going to be 6 root 5 times y1, which is 3. Actually, I'll do it in a different color so it makes it a little more visually appealing. So we'll do 6 root 5 times our y1, which is 3, plus 4 root 13 times our y2, which is 7, plus 2 root 13 times our y3, which is negative 5, all over 6 root 5 plus 4 root 13 plus 2 root 13. Okay. We're going to clean this up a little bit, so we're going to get negative 30 square root of 5 plus 4 square root of 13. I should do that and stay consistent with the colors. Now, because these two are root 13s, I can actually put those together. So we're going to get 18 root 13. Over, and I can combine those root 13s on the bottom. So we're going to get 6 root 5 plus 6 root 13. Then, over to the side, for our y, we're going to have 18 root 5. And then, so we're going to get 28 root 13 and then minus 10. So 28 minus 10 is going to be 18 root 13. Over, and we know what the bottom is going to be because it's the same. 6 root 5 plus 6 root 13. Okay, so this is where our incenter is located. Now, if we want to plot this on an actual coordinate plane to make sure that we're somewhat accurate in our calculation and it makes sense if we were to sketch our angle bisectors and see where they intersect, we're going to convert this over to a decimal using a calculator. So after plugging that into the calculator, we got negative 0.062 comma 3. Now this line previously would be like a simplified radical form of our incenter, where I'm leaving square roots in the denominators. I know that's traditionally not accepted, but ultimately we're converting it over to a decimal anyway so that we can accurately plot this. So let's go plot this on our coordinate plane negative. So just a nudge past the y-axis in the negative direction and then up to 3. So maybe somewhere around here. Now, if we draw in our angle bisectors, let's look to see if this is roughly accurate. So if I draw an angle bisector to A, so the slope of AB and the slope of AC are, one is rise is 4 and run is 6, so 2/3. The other one's negative 2/3, it looks like. So yeah, I could split this right through here. And then if I split this, it looks like roughly right. So this looks pretty accurate here for the incenter, where if I draw those lines, it looks like it's bisecting those angles if I were to estimate where they would be. And the intersection point does fall where our calculation predicted it should. So here is the value of our incenter. And that's how you do it. So you'll notice there's a lot of kind of messy square roots going on, and that comes as a result of calculating lengths of sides. So don't think you're doing things wrong. And it's not totally necessary to actually simplify these square roots because ultimately you're just going to plug it into a calculator. So if you're hesitant on those simplifications, don't worry about them. But I do want you to actually convert it over to a decimal at the end so that we can approximate the location and verify the accuracy of our calculation when sketching in the angle bisector. So there's an example done out, and that concludes this video.